So we're picking up where we left off from yesterday's lesson. We're going to decorate our picture to the best of our ability. We're going to determine the value of x knowing that these two triangles are similar. If I know two triangles are similar, I can use this scale factor, or I can use that idea of, okay, corresponding sides are going to be equal. We're going to see how ratios and proportions impact similar triangles or similar polygons. So if I notice RS and GH are corresponding, I could either use the name or I could use the picture because these triangles are not rotated. That is going to be equal to two other sides, but let's choose the side now that contains the x. So now let's use this side and this side. We've got RT containing the x and then GJ. Once we have this down, we're ready to put in the fractions.
So then we'll have to use the other side?
So the question was asked, how come we're not using ST and HJ? When we find a missing side, we only need one fraction from the picture. I could have used 8 to 12 instead of 10 to 15. All right, so let's cross multiply. Divide both sides by 15. So this missing side in the first triangle had to be a 6. So in this next example, we're going to still set up proportional sides. When we're given rectangles, we're only going to be given a few numbers because it's just assumed that the opposite side is the same as what's given. All right, so BC will be in relationship to LM, and that's going to be equal to the side DC to NM. We can put in the numbers immediately. So this is notes, right? In homework, we're not going to probably write this down. We're probably just going to set up the fraction 6 to 4 needs to equal x to 8. Cross multiply and divide. That's fine. I will need to see some sort of work, though. So we're looking at an answer of 12. That missing side needed to be 12. So perimeters of similar polygons. This is what we were talking about in the warm-up. If two polygons are similar, then the ratio of their perimeters will be equal to the ratio of their corresponding side lengths. So if you haven't written that down, they're going to be equal. So if we have a 3 to 2 scale factor or a 2 to 3 scale factor, the perimeters will also share that ratio. Let's go to this example. Copy it down. So the first thing we're going to do is find x using the strategies that we just did. Figure out a fraction of corresponding sides, and then use another fraction involving the x. If we take PQ and ST, we can have a fraction of 14 to 7. So we have corresponding side lengths of 14 to 7. That's going to be equal to the side lengths PR to SU, which is x to 9. We're going to cross multiply and divide to figure out this missing side length. So dividing by 7, we get that missing side length is 18. We may have been able to pick it out from the picture. Like, notice the jump from 14 to 7, 16 to 8. It's almost like we're dividing by 2, or it's like these numbers are cut in half. So it does make sense that if this side length is 18, yeah, 18 cut in half does make 9. So let's figure out the scale factor. Let's find a scale factor from this triangle to this triangle. So a scale factor, if we choose to use this side, 18, the scale factor is going to be written as 18 to 9. But wait a second, that reduces to a 2 to 1 ratio. And now let's find the perimeter of all. So add up all the sides in each piece. So we get a perimeter of 62 for PQR, and then what about STU? My bad? 48. So now we're going to figure out STU. So what's the scale factor, the perimeter from PQR to STU? If I look at the perimeter, 48, and then I look at the perimeter of 24, what's this scale factor? So if we divided both top and bottom by 8, wait a second. So since we realize we can reduce even further, we get a ratio of 2 to 1. I want to stress that the scale factor of side to side will become the same scale factor of the perimeters as well. We just wrote this rule down. This is proving that rule.